In April 2026, engineers sent a command toward the most distant machine humanity has ever built and waited almost a full day for it to arrive. The instruction was not designed to make a new discovery. It shut down one of Voyager 1's aging science instruments so the spacecraft could conserve enough power to keep listening to interstellar space. That detail matters because it immediately exposes the problem with one of the most dramatic claims now circulating about Voyager. The probe did not just discover a wall of fire at the edge of space. Nothing resembling a solid wall suddenly appeared in front of its cameras, and Voyager 1 has not carried an operating camera since 1990. The real event happened years ago, and the evidence arrived through particles, magnetic fields, and a faint electronic ringing in plasma. The accurate version is still astonishing. Voyager 1 crossed the heliopause, the boundary of the Sun's vast bubble of plasma, on August 25, 2012. Scientists did not announce that conclusion until 2013, after the spacecraft detected plasma much denser than the material it had been traveling through. That delayed confirmation is the reason the word confirmed belongs in this story. The word just does not. And the phrase wall of fire needs quotation marks. It is not an official name used by the Voyager team. It is a vivid metaphor for a boundary region where temperatures can reach tens of thousands of degrees, yet the matter is so thin that it cannot transfer heat the way hot air, flame, or boiling metal does on Earth. That contradiction is the center of the story. Voyager entered an environment measured at temperatures that would destroy ordinary material inside a dense atmosphere, yet the spacecraft did not burn, melt, or even feel anything like a blast furnace. The reason is that temperature and heating are not the same thing. Before that becomes clear, we need to understand what Voyager actually crossed. The Sun constantly releases a stream of charged particles called the solar wind. Those particles carry magnetic fields outward and inflate a gigantic protective bubble around the planets. That bubble is the heliosphere. The heliosphere is not a glass shell, and it is not perfectly spherical. It is a moving, changing region formed by the pressure balance between the solar wind pushing outward and the surrounding interstellar medium pressing inward. Solar activity changes. The interstellar environment is uneven. The boundary can shift, ripple, and respond to pressure waves moving outward from the Sun. The outer journey, therefore, has several stages. In 2004, Voyager 1 crossed the termination shock, where the solar wind abruptly slowed from supersonic speed and became compressed and heated. Beyond that shock lay the heliosheath, a turbulent outer layer of solar material. Farther still was the heliopause, where the Sun's plasma influence gave way to the denser plasma between the stars. Voyager was never designed as a dedicated heliopause mission. It left Earth in 1977 to exploit a rare alignment of the outer planets. A carefully chosen path carried Voyager 1 past Jupiter and Saturn, where gravity redirected it upward out of the plane in which most planets orbit. After the Saturn encounter, the spacecraft had no more planetary targets. Its speed and direction turned an aging planetary probe into an accidental interstellar laboratory. That history explains why every surviving instrument matters. The cameras that produced the famous images of Jupiter and Saturn were turned off in 1990 because there were no nearby worlds left to photograph, and power had to be conserved. From then on, Voyager's most important discoveries became invisible. They appeared as changes in electrical currents, particle counts, radio tones, and magnetic field vectors transmitted across billions of miles. Even the termination shock was difficult to locate because it moves as solar pressure changes. Voyager 1 may have approached and retreated from the shifting boundary before its accepted crossing in December 2004. The event taught scientists that the outer heliosphere was not a static set of concentric shells. It breathed in response to the Sun and the pressure of the surrounding galaxy. For nearly 8 years, Voyager 1 moved through that heliosheath. Its instruments recorded changing particle populations, declining outward flow, and a region far more complicated than the simple boundary drawings used in textbooks. Then, during a 13-hour period on August 25, 2012, the particle environment changed sharply and stayed changed. Lower energy particles associated with the heliosphere largely disappeared. Galactic cosmic rays from outside the solar bubble rose to their highest levels measured by the spacecraft. Those were strong clues, but one expected signal did not behave as cleanly as scientists had predicted. The direction of the magnetic field did not suddenly rotate in the obvious way many researchers had anticipated. That created a scientific problem. Had Voyager crossed into interstellar space, or had it entered one more strange layer inside the heliosphere? The team resisted the pressure to declare victory before the evidence was strong enough. They needed a measurement of the surrounding plasma density. Voyager 1 could not make that measurement in the normal way. Its dedicated plasma science instrument had stopped returning useful data years earlier and was formally shut down in 2007. The spacecraft still carried another instrument, however, called the Plasma Wave Subsystem. Instead of directly scooping up the plasma, it could listen for the characteristic frequency at which electrons vibrated. Nature supplied the missing experiment. A solar eruption sent a pressure wave outward through the heliosphere. More than a year later, that disturbance reached the region around Voyager 1 and made the surrounding electrons oscillate. On April 9, 2013, the plasma wave instrument detected a clear tone. The pitch revealed an electron density of about 0.08 particles per cubic centimeter. That was close to the density expected in the local interstellar medium and far above the density of the outer heliosphere. NASA described the plasma as more than 40 times denser than the material previously encountered in the solar bubble. Scientists then searched earlier records and found a weaker set of oscillations from late 2012. By combining those density measurements with the permanent particle changes on August 25, the Voyager team concluded that the spacecraft had crossed the heliopause on that date. The announcement came on September 12, 2013, more than a year after the actual crossing. That timeline is a model of how frontier science often works. An instrument records an event, the meaning remains uncertain, nature provides an additional test, and researchers revisit the older data with a better diagnostic. Confirmation can arrive long after the spacecraft has already moved beyond the place being confirmed. The delay also protected the mission from a false historic claim. Particle data alone strongly suggested that Voyager had entered a new region, but the stubborn magnetic field direction left room for another interpretation. The plasma density finally supplied a marker that was expected to differ dramatically across the heliopause. Once that marker appeared, the apparently conflicting magnetic result became a new scientific question, rather than a reason to reject the crossing. This distinction is essential for any headline using the word confirmed. Scientists confirmed the boundary crossing. They did not confirm a photographed wall, a literal flame, or a newly discovered object waiting at one fixed distance. They identified a transition in the physical origin and behavior of plasma around the spacecraft. This was not a single instrument spotting a bright object. It was a reconstruction built from particle counts, plasma waves, magnetic field measurements, timing, and expectations derived from heliospheric physics. The discovery was real precisely because the team allowed the evidence to resolve a confusing signal rather than forcing the data to match a dramatic headline. So where does the fire come from? To answer that, we have to separate three different environments that are often blended together online: the heated solar wind in the heliosheath, the heliopause itself, and the very local interstellar medium immediately beyond it. At the termination shock, the supersonic solar wind slows and heats. That creates hot, extremely thin plasma in the heliosheath. At the heliopause, the pressure of solar material and interstellar material reaches a boundary. Outside it, the local interstellar plasma is denser than the heliosheath plasma, though still incredibly sparse by any everyday standard. Voyager 1 proved that the density had changed, but it could not directly measure the plasma temperature because its plasma science instrument was no longer functioning. The famous temperature measurement came later from Voyager 2, which crossed the heliopause on November 5, 2018, at about 119 astronomical units from the Sun. Voyager 2 still had an operating plasma experiment. Its measurements showed that the very local interstellar medium near the heliopause was hotter than expected, around 30,000 to 50,000 Kelvin. Earlier models and observations had suggested roughly 15,000 to 30,000 Kelvin. That is the strongest scientific foundation beneath the wall of fire metaphor, but it changes the claim in two important ways. First, the direct temperature measurement belongs to Voyager 2, not Voyager 1. Second, a temperature of 50,000 Kelvin in a near vacuum does not behave like a 50,000 Kelvin furnace. Temperature describes the average kinetic energy of particles. Heating depends on how many particles strike an object and how much energy they can transfer. In a dense gas, enormous numbers of molecules collide with a surface every second. In the plasma near the heliopause, the particles may be individually energetic, but there are extraordinarily few of them. The numbers make that difference easier to see. The outer heliosphere can contain only around a few thousandths of an electron per cubic centimeter, while measurements outside the heliopause are measured in hundredths of an electron per cubic centimeter. The increase is enormous in relative terms and still leaves the environment vastly emptier than the best laboratory vacuums familiar to most people. A thermometer placed in a normal atmosphere reaches equilibrium through a flood of molecular collisions. Voyager receives no comparable flood. A charged particle can carry substantial energy, strike a surface, and contribute almost nothing to the spacecraft's overall temperature because the next collision may be separated by a large amount of empty space and time. The word fire creates another physical error. Fire is a chemical reaction involving fuel and an oxidizer, usually producing hot gases, light, and new chemical products. The heliopause has no burning sheet of fuel. Its plasma consists mostly of ions and electrons whose motions and fields are governed by electromagnetic forces. Calling it fire describes emotional intensity, not the mechanism. Nor would a human observer see an orange or blue glow around the spacecraft. Visible glow requires enough excited particles to emit a significant number of photons into the eye or a camera. The local interstellar plasma is too diffuse to create a luminous curtain. Voyager crossed darkness, and only its instruments revealed that the darkness had changed. Imagine the difference between being hit by one fast-moving grain of sand and being buried in a high-speed sandstorm. The speed of each grain matters, but so does the number of grains arriving. Near the heliopause, the particle count is so low that the spacecraft does not absorb enough thermal energy to be cooked by the plasma. NASA's own educational material makes this distinction explicit. Even when particle temperatures are high, the density can be so low that a massive object such as a spacecraft does not feel that temperature in the familiar sense. Voyager's thermal condition is controlled far more by its own power system, radiation balance, and the fading warmth of its equipment. There is also no wall. Voyager 2's direct observations showed a broad plasma boundary region extending roughly 1.5 astronomical units before the heliopause. Inside that region, the plasma slowed, heated, and became denser. A much thinner layer began about 0.06 astronomical units inside the boundary, where density and magnetic field strength increased. The actual heliopause transition observed by Voyager 2 occurred in less than 1 day. That is sharp on the scale of the heliosphere, but it is not a material surface. A spacecraft cannot touch it, scrape against it, or photograph a glowing barrier. It is a change in the behavior, origin, density, and magnetic environment of particles. The comparison between Voyager 1 and Voyager 2 revealed that the boundary is not identical in every direction. Voyager 1 crossed at about 121.6 astronomical units in the northern hemisphere of the heliosphere. Voyager 2 crossed at about 119 astronomical units in the south. The structures each probe encountered were different. The separation between the two crossings gave scientists something one spacecraft could never provide: a crude comparison across the global heliosphere. The probes moved through different hemispheres at different phases of the solar cycle, along different magnetic geometries. Their crossing distances were similar, but the detailed sequence of particle and field changes was not. That result matters because models of the heliosphere must explain both local measurements at once. A model that reproduces Voyager 1 but fails at Voyager 2 is incomplete. The two paths constrain the shape of the boundary, the way the interstellar magnetic field drapes around it, and the pressure carried by particles too energetic to behave like an ordinary thermal gas. The observations also challenged the old image of a blunt bow shock standing permanently in front of the heliosphere. Measurements from other missions suggested the Sunday may move through the local interstellar medium too slowly to form a classic strong bow shock. The frontier is better understood as a complicated interaction region whose global shape remains an active research problem. Voyager 2 found a magnetic barrier just inside the heliopause and a relatively thin, simpler crossing. Voyager 1 experienced precursor regions where interstellar particles appeared before the final crossing. In both cases, the magnetic field direction changed much less than many researchers had expected. That small directional change became one of the most important surprises. The heliopause was not acting like a clean dividing line between two unrelated magnetic systems. Instead, the measurements suggested a connected, distorted region where fields and particles interact around the surface of the heliosphere. The boundary also responds to events from the Sun. Coronal mass ejections and merged pressure fronts can travel for months through the solar wind, cross the heliosheath, strike the heliopause, and transmit disturbances into nearby interstellar plasma. Voyager 1 has detected the resulting plasma oscillations far beyond the crossing point. This is why saying the spacecraft has entered interstellar space does not mean it instantly entered a perfectly undisturbed galactic environment. The Sun still influences the nearby region through magnetic structure and traveling pressure waves. Scientists expect Voyager to move gradually into more pristine interstellar conditions, but the exact distance required remains uncertain. The measurements since 2012 have transformed the heliopause from a theoretical line into a dynamic physical system. Voyager 1's plasma wave data initially captured occasional whistles caused by strong disturbances. Those events were useful but irregular, often appearing only about once a year. Researchers later identified a much fainter, nearly continuous plasma wave emission in data beginning around 2017. That subtle tone offered a way to track changes in electron density over a long stretch of interstellar space, rather than waiting for a large solar shock to make the plasma ring loudly. The record showed density rising after the heliopause crossing and reaching a roughly stable range by the middle of the decade, with continuing fluctuations. The interstellar medium did not look empty or silent. It behaved like a thin ocean carrying waves at many scales, including disturbances launched by the Sun and larger turbulence within the galaxy. Plasma density is not merely a descriptive number. It helps determine how waves travel, how pressure is balanced around the heliosphere, and how the sun's magnetic bubble responds to the surrounding medium. The boundary protects no planet like a solid shield, but it changes the pathways of charged particles entering from the galaxy. Galactic cosmic rays are high-energy particles accelerated by events such as supernova remnants and other powerful processes in the Milky Way. Inside the heliosphere, the solar wind and magnetic field alter their intensity and direction. Voyager's particle measurements before and after the heliopause therefore help scientists understand how a star's extended atmosphere modulates the radiation environment around its planets. That connection does not mean a ripple at Voyager produces an immediate hazard on Earth. The spacecraft is measuring the outer boundary conditions of a vast system. Those measurements improve models of heliophysics, stellar winds, and astrospheres around other stars, rather than issuing a forecast of a sudden event at home. That is a better mystery than a literal wall of flame. Voyager is not reporting a single frozen boundary. It is mapping how a star's atmosphere ends, how its magnetic shield meets material from other stars, and how that meeting region changes with time and direction. The phrase edge of space also needs correction. Space does not begin at the heliopause, and the solar system does not simply end there under every scientific definition. Voyager crossed the edge of the heliosphere, the region dominated by the solar wind's plasma and magnetic influence. The sun's gravity extends far beyond that boundary. NASA notes that Voyager 1 will need roughly 3 centuries to reach the inner edge of the Oort cloud, and perhaps about 30,000 years to travel beyond that distant reservoir of icy bodies. So Voyager is in interstellar space while still remaining gravitationally inside the broader solar system. This sounds contradictory only because different boundaries answer different questions. The heliopause tells us where the solar wind stops dominating the plasma environment. The Oort cloud describes the distant gravitational architecture of the solar system. A spacecraft can cross one frontier while remaining unimaginably far from the other. There is another correction hidden inside the word confirmed. Voyager 1 did not discover the concept of the heliopause in 2012. Scientists had predicted such a boundary for decades. The Voyager spacecraft detected radio evidence linked to the heliopause as early as the 1990s, long before either probe physically reached it. What Voyager 1 accomplished was the first in-place crossing and measurement of interstellar space by a human-made object. Its particle changes and plasma density evidence turned a predicted boundary into a location that had actually been sampled. Voyager 2 then supplied the complementary measurements Voyager 1 could not make. Together, the two probes showed that the heliopause has different local structures, that plasma density jumps dramatically across it, that the nearby interstellar plasma can be hotter than expected, and that magnetic fields remain unexpectedly aligned across parts of the transition. No single result justifies every version of the Wall of Fire headline. The temperature is real. The boundary is real. Voyager 1's crossing is real. But the direct 30,000 to 5000 Kelvin measurement came from Voyager 2. The confirmation is more than a decade old, and the word fire describes neither flames nor dangerous heating of the spacecraft. That does not weaken the story. It makes the survival of Voyager scientifically understandable rather than magical. The probe did not endure impossible heat through extraordinary shielding. It passed through a region where energetic particles were too sparse to deliver destructive thermal power. The greater threat to Voyager today comes from time and electricity. Each spacecraft relies on radioisotope thermoelectric generators whose output declines by about 4 watts every year. Mission engineers have spent decades turning off heaters, subsystems, and instruments in a carefully planned sequence. The radioisotope generators do not operate like rechargeable batteries. Heat from the decay of plutonium is converted into electricity, and both the fuel's decay and the aging of the conversion system steadily reduce available power. Engineers cannot send a repair crew, install a new panel, or rotate the spacecraft towards stronger sunlight. At Voyager's distance, solar panels would be essentially useless for a mission of this design. Every shutdown is therefore a trade. Turning off an instrument ends one type of measurement but can preserve communication, thermal control, and the instruments judged most valuable for the remaining interstellar mission. The sequence is planned years in advance, then reconsidered as real power margins, temperatures, and component behavior change. Voyager's age creates risks beyond electricity. Thrusters, heaters, memory, telecommunications hardware, and attitude control systems have all operated far longer than their original planetary mission required. Engineers have repeatedly found ways around failures by using dormant hardware, altering software, and commanding systems under conditions that could not be fully reproduced on Earth. On April 17, 2026, the team switched off Voyager 1's low-energy charged particles experiment. That instrument had operated for nearly 49 years and helped measure ions, electrons, cosmic rays, pressure fronts, and changing particle regions beyond the heliosphere. Shutting it down was not a scientific preference. It was a power decision. Voyager 1 still had two operating science instruments after that command, the magnetometer and the plasma wave subsystem. One measures the magnetic environment, the other listens to plasma waves, including the faint signals that helped prove the spacecraft had entered interstellar space. The spacecraft was more than 15 billion miles, or about 25 billion kilometers, from Earth. Commands required roughly 23 hours to reach it, and the response needed roughly the same time to come back. Every engineering action therefore unfolded across nearly 2 days of silence. Later in 2026, Voyager 1 is expected to become the first human-made object to reach a distance of 1 light day from Earth. That milestone does not mean the spacecraft travels at the speed of light. It means radio waves moving at light speed will require 24 hours to cross the gap in one direction. At that distance, a weak signal from a transmitter built in the 1970s must be received by giant antennas on Earth, decoded, checked, and compared with the expected behavior of equipment operating far below its original design temperatures. The remarkable current story is not that Voyager has suddenly found a new burning wall. It is that the machine remains scientifically useful at all. Power management now determines how long that usefulness can continue. NASA's team is testing more ambitious ways to reduce electrical demand while keeping the spacecraft warm enough and stable enough to communicate. Every saved watt can extend the period during which Voyager samples a region no other operating spacecraft can reach. The remaining instruments are particularly valuable because the local interstellar medium is not uniform. Density changes, magnetic fields bend, pressure waves arrive from solar events that happened many months earlier. Voyager can watch those disturbances evolve at distances where no replacement mission exists. The magnetometer can test whether the field continues to relax toward the direction expected for the less disturbed interstellar medium. The plasma wave instrument can track electron density through strong oscillations and the weaker continuous emission. Together, they preserve the two measurements most central to the frontier Voyager crossed: fields and plasma structure. What they cannot do is provide a complete weather station for interstellar space. With particle instruments shut down and the original plasma detector unavailable, the remaining picture is narrower than it once was. Scientists must combine the surviving data with earlier Voyager records, Voyager 2 measurements, remote observations, and physical models. That limitation should be visible in the documentary rather than hidden. Voyager remains unique, but uniqueness does not make every inference direct. Some quantities are measured at the spacecraft, some are reconstructed from wave frequencies, and some are inferred by comparing models with both Voyager crossings. Eventually, one instrument after another will fall silent. The radio signal itself may disappear while Voyager continues moving through the galaxy. The spacecraft will not stop at the heliopause, at 1 light day, or when its power drops below the level required for communication. That future gives the Wall of Fire story its most powerful final image. Picture a machine launched when home computers were rare, now traveling through plasma that came from the space between stars. Around it, particles with temperatures measured in tens of thousands of Kelvin pass through an almost empty darkness without producing flame or glow. 2 slender antennas listen for electrons ringing. A magnetometer records the field draped around the sun's distant bubble. 23 hours later, the information reaches Earth as an impossibly faint radio signal. Voyager 1 did not just discover a literal wall of fire. Scientists confirmed something more precise and more important. The spacecraft crossed the heliopause in 2012, entering a hot, thin, dynamic frontier where solar material gives way to interstellar plasma. The wall is a metaphor. The heat is real. The survival is physics, and nearly half a century after launch, Voyager is still telling us what the edge of our sun's influence actually sounds like.